Hey folks, this is Major Jones here to talk to you about shift registers. So this is an application of D flip-flops that is super useful. Previously we saw how we can use D flip-flops to build counters and finite state machines, and now we're going to build some shift registers. All right. So the basic idea of a shift register is that I want to be able to do, I want to shift a sequence of bits, one sort of position at a time, and in particular, I want to be able to do potentially sort of a parallel to serial conversion or a serial to parallel conversion. So you can see here that I might have this parallel to serial device that I want to be able to kind of convert. In this case, 4 bits that are all present on 4 different lines all at the same time. I want to convert that into a sort of serial bit stream where each bit occurs sort of on each clock cycle on the same line. Or I might want to go the other way, right? I might have data that is on a single wire. That's where I've got 1 bit corresponding to each clock cycle, and I want to be able to ship those in and then read all 4 bits out at the exact same time. I want to do my serial to parallel conversion in that case. And you can see here, kind of on the right-hand side, some waveforms depicting these. See if I can zoom out. These kind of sample data, right? So on the top here, if I'm loading the value 1011 all at once to my parallel serial converter, I want those bits to come out one at a time. And so you can see, starting at time 0, I'm looking at the least significant bit here. That's a 1, followed by a 1, followed by a 0, which is this bit here, followed by the most significant 1 right here in kind of the last time frame. And it looks a little backwards, right? But keep in mind that this is showing time going all the way, from left to right. So I'm looking at, again, the least significant bit here in time 0 and the most significant bit here in time 3. For serial to parallel conversion, right, I've got values that kind of come in 1 clock cycle at a time, and they're going to sort of shift their way into my 4 output lines, so that it's on this last clock cycle that my piece of serial data 0110 is present all at the same time on my outputs. You can see here 0110 is present in clock cycle 4 on the output of my shift register. So let's take a look at how we actually build these in real life. So you can see here, this is an example of that first unit, a parallel to serial converter. What I want you to notice is that I've got a series of D flip-flops, right? And the output of each flip-flop is connected to the input of the one to its right. So you'll notice, actually, let's do this. So I've got, if I put like a 1 here in this flip-flop, when I toggle my clock, right, the 1 is here present on this input to my next flip-flop. So on the next positive clock edge, right, that 1 gets loaded into this second flip-flop. And the value on this leftmost flip-flop is just sort of hard-coded to a 0. So this would be a 0 that sort of fills in. So on the next positive clock edge, that 1 kind of transfers to the flip-flop to the right. Now it's this flip-flop, right, the third one that is seeing that 1 input. So on the next clock cycle, right, that 1 bit is going to move 1 more to the next flip-flop. If I toggle again, this 1 will go to my last flip-flop, and I'll get that sort of bit now on my serial output. And if I toggle my clock one more time, that's 4 clock cycles, I've shifted my bit all the way out of my shift register. So this is really useful for taking 4 or more bits that are all in parallel, and putting that data onto a single line. All right, so let's see one more example here. Where I'm going to show. I'm going to do 1 1 0 1. All right. So you can see when these bits are loaded into my flip flops, the serial data line shows initially sort of that least significant bit, and now in each clock cycle, that value is going to shift 1 to the right. So now my register has the 110 value, which were the upper 3 bits. Now the 11, now just the most significant bit, and now that 4-bit value has shifted out of my flip-flops. All right. There's a couple different ways to load data into the flip-flops here. I've left that off of this circuit to kind of keep it uncluttered, but we can take a look at in class kind of how that's done, how I might actually load some values into these flip-flops. All right. Next is serial to parallel conversion. I want you to notice the topology of these flip-flops is the same, right? I still have the output of one flip-flop connected to the input of the one to its right, okay? The difference is, I'm going to send data into this flip-flop, 1 bit at a time, and then I want to be able to read all 4 bits out once it's finished. So I've got this input here, which is my serial data, And then I got this weird little bit up here that's kind of gating my clock signal. And we'll talk about kind of why that's important in maybe just a sec. So let's start with just kind of seeing this in operation. Let's say I want to shift in the value. I want to do like a uh, one. Well, we'll do a 1001. Right. So I'm going to start my clock signal toggling. Okay, so there's a 1 on this data line. I'm going to hold down my strobe button to let that 1 sort of latch into this first flip-flop. All right, the next 2 bits are zeros, so I'm going to change my serial data line back to a 0. I'm going to try to grab 2 clock cycles here. Boom, boom. Okay, so I got 2 zeros loaded into my flip-flops. And the last bit I want to be a 1. So then I'm going to hold this strobe signal to get a 1 in here. And so now my 4-bit value is in my shift register, right? 1001. It happened 1 clock cycle at a time, but now they're all available on my outputs here. Which is useful for taking sort of data that's been packed right under a single wire and it's sort of expanding it out into now multiple data lines that I can operate on all at the same time. And maybe at this point you can start to see the reason for this gate here, which is previously for my parallel to serial shift register, I could once that data was loaded, I wanted it to go out 1 bit at a time. It didn't really matter if this clock was free running. Once my data was all the way out. But for this register, it really does, right? I want to be able to execute 4 clock cycles exactly that kind of correspond with my serial data input bits. But as soon as all 4 bits are in my shift register, I don't want my clock to keep toggling, right? Because I don't want those values to sort of run off the end of my shift register. So we call it strobe. Strobe's a signal name here, but the idea is that this strobe signal is going to be high for exactly 4 clock cycles to let exactly 4 bits into the shift register from the serial data line. But then as soon as I've got my 4 bits, then the strobe signal kind of goes low to disable the clock. And so now you can see that even though the clock is running, I can take all the time I want, digitally speaking, to read this parallel data output. Okay, the last circuit we're going to look at is called a ring counter or a recirculating shift register. And you'll notice, again, same topology, right? I got my output of one flip-flop connected to the input of the next. Only in this case, I've got the output of my last flip-flop, all the way on the right-hand side, is connected all the way back around to the input of the first flip-flop. So let's see what's going on here. Right? If I load a single bit into this leftmost shift register, on each clock cycle, it's going to move 1 to the right. When it gets to this last flip-flop, right, look at this. That bit is now present on the input to the flip-flop on the left. So instead of falling off the end of my shift register, it circles back around on the next positive clock edge. That 1 gets loaded back into the leftmost shift register. And this is useful for creating a number of sort of repeating patterns, right? I might have a 1 that I just want to shift through these each of these registers. So if my clock is kind of running on each clock cycle, right, that bit just kind of shifts its way around and then works its way back to the front. And so we could we could conjure up circuits where the values for this shift register are loaded, sequentially, like serially or parallel. So it's kind of this one's kind of a circuit that it's an example of, has elements of both the parallel to serial and serial to parallel conversion. All right, so hopefully at the end of this lesson, hopefully now you are refreshed the idea of parallel and serial data, and we'll talk more in class about some actual computer usages of sort of converting from one to the other. And hopefully at this point you can also sort of identify, or you can actually build yourself any of these 3 circuits: parallel to serial conversion, serial to parallel, and ring counting or recirculating shift register. And you can also sort of draw in a waveform maybe kind of how data is moving through this shift register. That's all I got, folks. See you next time.